All right, so we're going to take a quick introduction to chemical bonding to follow up what we were doing before break with oxidation states and talking about the octet rule, where different elements will gain or lose electrons to satisfy that full outer shell. For chemical bonding, we're referring to a strong enough force of attraction between two different atoms or two different ions that causes them to function as a single unit. Wherever one goes, the other goes with it. In general, there's three different types of chemical bonds: ionic, covalent, and metallic. That comes down to the combination of atoms that are bonded together and how their level of attraction compares to one another. Chemical bonds are often misspoken of in regards to intermolecular forces. So, for example, with the case of water, an intermolecular force is the force like hydrogen bonding that holds one water molecule towards another water molecule. But it's not the chemical bond itself, it's just this interaction between them. So, for example, here if we had one water molecule and a second water molecule somewhere else in the container, this here is a chemical bond. It's the covalent bond in this case that holds the oxygen and the hydrogen together in the same water molecule. It's incredibly strong, whereas the hydrogen bond would be this attraction between the hydrogen of one water molecule and the oxygen of another. And that interaction, that attraction, is much more temporary. It just loosely holds them together, and it can change and shift from one to another. But it's not a chemical bond because those two water molecules can move independently of each other. Now, for the three different bond types, like I said, it comes down to the level of attraction and the comparison of what two things are with each other. So if we look at this first example here, where we have fluorine and fluorine. So here we have two nonmetals, and what we learned about last week was that these nonmetals have a really high level of attraction, so high that they tend to pull electrons in towards themselves to make a chemical bond. So this fluorine atom here on the right, with its 9 protons and 2 energy levels, has this empty spot on its orbital that it can pull in another electron towards because it has a high level of attraction. So when it is next to another fluorine atom, such as the one on the left here, it's going to be pulling and attracting that electron towards itself. However, the level of attraction in this atom is very similar to the level of attraction in this atom because they're the same exact element, which means that while this fluorine on the right is pulling on that electron, the element on the left, the fluorine, is also going to be pulling backwards. It's not going to be able to relinquish or let go of that extra electron. So what ends up happening is not only does this electron here again get pulled toward the left, but this fluorine on the left also has a missing electron in its outer orbital that it can attract and pull an electron towards as well. So let's represent these really quickly as Lewis dot diagrams to make things a little bit clearer and easier to see. We know that fluorine has 7 valence electrons, and there's those 2 atoms. So we can represent them like this. And what we see is that this fluorine on the left is going to have its electron pulled to the right, and this electron on the right is going to be pulled to the left. To the extent that these 2 fluorine atoms then are going to end up coming next to each other, and those 2 electrons that are interacting between the two, one being pulled left, one being pulled right, are going to end up in between those 2 fluorine atoms. And they're going to be stuck in this tug of war, where they're attracted to the left, they're attracted to the right, almost equally as strongly, which means that neither one is going to lose it, neither one's going to gain it. They're going to be fighting over them in this mutual attraction. And this is called a covalent bond. So we often say that these electrons here are being shared between the two, but it's not really sharing in the friendly sense that we normally think about, where you're giving something to this person and then they're giving something back. They're really just fighting over those 2 electrons. One's pulling one way, one's pulling the other. It's like a big tug of war. But nobody can win in this case because they're each pulling equally as strongly. On the other end of the spectrum, we have something like this, a second example here, where we have fluorine again, but now we have lithium. Lithium's a metal, and what we learned about with metals is that they have a really weak attraction to their outer electron shell because in this case there's only 3 protons compared to fluorine's 9. So what that means is if we represent those two atoms with their dot diagrams, fluorine with its really strong level attraction is going to pull on that electron again. It's going to draw it into that empty space on its outer orbital. Lithium's really weak. It's not going to be pulling on anything from fluorine. So it cannot compete with its 3 protons compared to fluorine's 9. So what ends up happening is that after this pull occurs, lithium's going to end up with 1 less electron, and fluorine is going to have 1 extra. So there's the original 7 there in black, plus the 1 new one it gained, which gives it a -1 charge. So this here with the electrons themselves didn't cause a bond. It didn't tie them together the way the covalent bond did. However, what it did do is create 2 oppositely charged particles. Now what we know about Coulombic forces is that oppositely charged particles are going to attract each other. So this attraction between these 2 different charged particles is what we call an ionic bond. And then in our last scenario, we see where we have 2 metals, such as 2 atoms of lithium. So this would be like that little piece of lithium metal that was dropped into the water in the chemical reactions video. Now lithium again has a really weak attraction. So if we have these 2 lithium atoms next to each other like this, we know that the lithium atom on the left has a weak attraction for that electron. The lithium atom on the right has a weak attraction for that electron, which means that this electron is free to kind of leave and go towards this one, but it's not going to go all the way to the lithium atom because the other one's not pulling on it strong enough. Just like this electron here can kind of leave and go wherever it wants, but it's not going to get locked into the lithium on the left because, again, it's not strong enough. So what ends up happening is these valence electrons, when we have only metals around, these valence electrons are free to kind of move around between these different atoms without getting locked to any single one of them. This creates what's known as a sea of electrons. And so essentially there's this big negative electron cloud that moves between all of these different metal cations because each individual one will lose that electron as it roams freely throughout the whole sample. So this is what we call metallic bonding. We'll go into more about each of those different types as we go into the next couple videos.